So let us begin with lecture 5 of our course on astronomical data analysis using Python. We will continue our discussion on Python modules, which we sort of left halfway in the last class. So amongst Python modules, there are 3 types of modules that you will encounter. The first are built-in modules. They come with all standard installations of Python. You don't have to do anything special. The moment you install any distribution of Python on any operating system, you are guaranteed to have those built-in modules installed. We'll look at a little bit in more detail on what the built-in modules allow you to do in a few minutes. But those are installed. And we have encountered some of them. For example, early on in the course, we encountered the math module. So that math module is a built-in module. It's guaranteed to be available with every Python installation. Then there are third-party modules, and these need to be installed separately. So Python's built-in modules are a small fraction of the total number of modules available for Python. The overwhelming majority of modules that you will encounter are what are called third-party modules. They are not installed by default when you install Python. Although there is a bit of a confusion, because if you install a distribution like Anaconda, for example, it will install not just the core Python, but it will also install a fairly large number of third-party modules by default. And then you can install even more using the package management software that's available as part of Anaconda. The third kind of modules are the modules that you will write yourself. So initially, you may write a module for your own use, and later on, you may feel that this is a module that other people may find useful. And then you may put in a little more effort and convert your module into a third-party module and make it available publicly so that other people can download and use your code with its functionality. So we are going to look at how modules are made in Python, how to make your own modules in Python. And it's really very, very simple. We are going to look at the simplest kind of module that you can construct in Python. A little bit later on, I will discuss how you can make a full Python package, okay, with its own classes and modules and so on. But today we are just going to look at the simplest module possible and how you can construct it. Built-in modules in Python are numerous, and they constitute what is known as the Python standard library. Now, what is this Python standard library? Python standard library is a collection of modules that are installed with any Python installation. The built-in functions that you encounter, for example, like print and type and length and so on, are part of the built-ins module, which is one of the built-in modules of Python. But there are numerous others. For example, there is something called sys, which contains tools for reading in system arguments and parsing them, operating system information, etc. Then there is the OS module for handling files, directories, and executing external programs and so on. There is a module called RE for parsing regular expressions. For handling date and time conversions, there is a module called datetime. There is a module called CSV for reading and writing of CSV tables. What are CSV tables? CSV stands for comma separated value. So this is the simplest kind of data file you can construct, where you have a number of rows and each column is separated by a comma. We'll look at some of those CSV files in the assignment. Besides these sort of commonly used modules, which I've listed here, There are more than 100 others that allow you to do many different things, ranging all the way from text processing to networking and inter-process communication, handling of data on the internet, and much more. Although these modules are very powerful, they're very numerous, it turns out that there are no built-in modules for advanced mathematics or big data handling. And these are the kind of things that we are going to need when we use Python for astronomical data analysis. So this, in the second half of this course, we are going to see how this major deficiency in Python, as in the core Python installation, can be rectified by the addition of third-party modules. But right now, for the Python standard library, there's lots. And before you start looking for a module that provides a certain functionality that you need, you are encouraged to look through the modules. Just be familiar with the modules in the Python standard library and see, before you look elsewhere, see whether the Python standard library provides some or all of the functionality that you need. And there's a fair chance, unless you're dealing with real hardcore mathematics, statistics, big data handling, and so on, if you're just want to move files around, you want to rename files, you want to do things like that, the Python built-in modules should be sufficient. To learn more about the Python standard library, I have provided a URL at the bottom of this slide. Please go to this page on python.org and look at the list of libraries that are available and see what kind of functionality they provide. Now we come to the third-party modules. These are modules that, as I said, need to be installed separately. There are probably hundreds of thousands, actually there are hundreds of thousands of modules in every imaginable area of computing. Given the length of this course, we are going to learn about a handful of them. And again here, like before, we are going to follow a philosophy that we will only learn the bare minimum that we need in order to carry out data analysis in the field of astronomy. If there are other modules that serve other people's purposes, we are not even going to look at them. So what are the modules that we are going to look at in some detail? We've heard the name NumPy a few times in this course. So we are going to use a module called NumPy that allows fast array processing in Python. And we are going to also look at briefly a module called SciPy that provides a number of scientific routines that are useful for numerical computing in general, and some of them are also useful in data analysis and statistics. So we'll look at those. We will also look at how Python can be used for making plots and figures, because naturally that's the most common way that we all use to visualize our data. In order to do that, we are going to use a module or a package called matplotlib, which I will cover in a separate dedicated lecture. There are many other modules which are useful for data analysis. For example, there is a module called Mayavi, which can be used for plotting 3D stuff and making animations of complicated objects. Then there is a module called Pandas, which is very useful for tabular data analysis. But we are not going to cover that because it is, we are going to cover tabular data analysis using AstroPy, which is also a fairly powerful module for handling tables and images. AstroPy is basically Python for astronomers. It adds functionality to Python that astronomers expect. Okay, so for example, astronomers want to display images, they want to change image scales, they want to convert, let's say, galactic coordinates into equatorial coordinates or vice versa. So all of that functionality is embodied in this module called AstroPy, which again we are going to look at in some detail. Now, as many of you are aware, through the virtual observatory effort, there is now a vast amount of data that has become available to astronomers to use. Now, when astronomers have to use data, first they have to search for data, and then perhaps they want to download the data and use it in their analysis. A module that provides this functionality is called AstroQuery, and it allows you to access and download data from large astronomy data repositories. Okay, these may be repositories of images, of spectra, of data cubes, or even catalogs. All of these can be searched for and downloaded onto your computer so that you can combine data perhaps from multiple telescopes, perhaps operating at multiple wavebands, and do a complete multi-wavelength analysis of the objects that you are trying to study. So AstroQuery is very, very powerful. It has grown increasingly powerful over the last 2 or 3 years. And we are going to look at a few examples from AstroQuery in the lectures, but we are also going to have a few questions in the assignment, which will require you to use AstroQuery. And that will really get you started on using on doing astronomical research using public data in these large data repositories. There is also a module called Scikit-learn, and Scikit-learn is contains machine learning and classification tools for Python. It is quite popular in the machine learning community. So if your inclination is towards using data science, machine learning and AI techniques, then you should definitely take a look at Scikit-learn. But it is the modules in bold font are the ones that I'm going to cover in this course. The ones that are not bold are something that I'm going to skip over, but definitely something that will be of interest for you. As already mentioned, third-party modules will need to be separately installed. And this is most easily done via a program called PIP, P-I-P. And please go to this web page that I've given here and look for installation instructions on how to install Python modules, additional third-party modules using PIP. Before you install a module, you may want to look at what kind of modules are available. So these are listed, all the third-party modules are listed at this website called pypy.org, which has, as of now, more than 340,000 modules available. And this includes 651 astronomy packages. So that really is quite impressive. It's a testimony to the fact how popular Python is in general, and specifically within Python, how popular astronomy is, that there are a large number of useful packages available. So suppose you want to now make your own module. You have looked at the built-in modules, you have installed some third-party modules that you liked, but you say, no, I want to start making my own module. And that is almost ridiculously simple to do in Python. You just open a file, give it some name, mymodule.py, let's say, and write code, Python code in that file. If the file is in the present folder, which means your current working directory, or in folders that are located in the environment variable Python path, then something like the following will work. Import my module, and my module dot sum method. You'll be able to use the functions within that module in this way. Please note the following. When you make your module must have the extension .py. But while you're importing the module, the extension must be dropped. Both of these things are required. If instead of .py you put .py2 or .p or something, it won't work. And while importing, remember you have to drop the .py extension. The third note is, although you can, do not create modules with the same name as modules in the Python standard library. So don't create modules, don't create a module called math, for example. Okay, if you want to create a module called with all your mathematical functionality in one place, you by all means create it, just don't call it math. Okay, you could call it my math module or my math or whatever else. So here is an example of a module. It's a custom designed module. It's stored in a file called example.py on my computer, on my working directory, and it contains some functions for the purpose of demonstration. Okay, so you can define a function called def fun1, that's my function 1, and all it does is it prints inside fun1. And then there is another function which just prints inside fun2. Of course, this is for the purpose of demonstration. When you write your own code, your fun1 and fun2 will probably do something more useful. Then there are two variables that are defined in this module. Pi is equal to 3.14 and e is equal to 2.7. And it says print I am a custom module. Okay, there is a small error here. This should be enclosed in brackets. The reason this typo survived is because it's from an older version 2 slide. And so remember that those double quotes need to be enclosed. The print has to have a open parenthesis and close parenthesis enclosing that statement. The above code is stored in a file on my computer called example.py, and let's see how to use it. In order to use it, you just type import example. And if you type import example, what does it do? It's just going to print out the print statement. Okay, and it's going to print I am a custom module. And the definition of the functions, etc., has happened. But since they don't produce any output just yet, unless you call them, nothing got printed out. So here we are illustrating that any output generated by example.py will appear on the screen. Okay. So if I do print example.py, it will print it. And then if I run example.fun1, which is my function 1, it's simply going to print inside fun1, right? So now notice here that we have available both the properties of the module example. Remember, we defined two variables inside there, pi and e. Those are available to me, and the functions within it are also available to me, and they are to be called by typing example dot the name of the function or the name of the property. Not only that, I can type something like help example and I get help on the module example. So it says the name is example and the description is a custom module containing some functions for the purpose of demonstration. It lists which functions are available, fun1 and fun2. It lists under data what variables are defined within that module. So example.e and example.py in this case. And it even tells you where the file that contains or that defined this module is located on my file system. Notice the description over here. Where did this come from? It came from whatever text we had enclosed in the doc string at the beginning of the module. So if you jump back to the module itself, you'll see this triple quoted string, multi-line string that we had put at the top of example. That got automatically picked up when this help documentation for this module was auto-created. Remember, we didn't have to, we just wrote the module. We did not write this functionality. This kind of automated documentation creation via the help function happens automatically in Python. You don't have to do anything separate. So now we are done with modules. And over the next 10 minutes or so, 15 minutes or so, I'm going to cover some aspects which are important in programming, but have not been already covered. So the first thing that I would like to talk about is the assert statement. So here is L is equal to something, some list, A is equal to 5.0. I would like to point out something that I didn't mention earlier, which I should have, is that variable names in Python are case sensitive. So capital L and small l are different variables. Capital A and small a are different variables. So please be careful. Standard practice usually is to use small letters for variable names. We'll talk a little bit more about variable names later on in this lecture. Now we come to the assert statement, right? What does the assert statement do? It has two parts. It says assert and then is assert some condition, something that will evaluate to true or false. And if it evaluates to true, then nothing happens. The program goes on. However, if it evaluates to false, the program stops and gives an assertion error. Okay. The second assertion statement is type A is type ... which means type of string. So it asserts that A is a string, and obviously A is not a string. So if that fails, it's going to print requires a string. So when I run this program, there are actually two assertion errors in this code snippet, but the program crashes or stops and gives me a traceback to an assertion error, and helpfully it prints out not enough data points. Okay. I urge you very, very strongly to use the assert statement, use these assertions liberally in your program. They make debugging of complicated code very much easier than it would otherwise be. These are particularly useful as interface just before, for example, a function is called, right? And why is that? Because let's say you are trying to fit some data, okay? And suppose your fitting algorithm really needs at least 10 points for your fitting process to work. Now, if you just put an assert, and suppose you're doing this fitting within a function, okay? It might be called fit my function or fit my data. So before you pass your array to fit my data, you must have an assert there which asserts something like this. If L is your data list, assert len L is greater than 10. Because if it is not, it is better that you stop right here. Because if you go forward and instead of sending 10 points, you send only 4 points or 5 points, obviously your fitting is not going to work as expected. It may go into a loop, and then eventually after a lot of computation, your function may return an error saying that I don't have enough points to fit. Whereas if you put in an assert statement before you call the function, you'd save a lot of compute time in the process, because you will never enter the function. Before enter the function, you'll get an assertion error and the program will stop. So therefore, I strongly urge you to use the assert statement. I believe it is one of the most important components of a style of programming called defensive programming. And in defensive programming, what we do is we assume that things will go wrong, something or the other will break in our program, and we use asserts to make sure that things don't break, or if they break, we are going to stop, reassess, and then move forward. Another way of handling problems with your code is via what is called as the try except structure. Okay. So whenever there is an error in your Python code, something that is not allowed you try to do, Python returns what is called as an exception. And we have encountered exceptions. In fact, the most recent exception that we encountered is this assertion error. And Python allows you to handle those exceptions formally within your program. Because sometimes you want to do something if an exception occurs, something else if an exception doesn't occur. The structure that Python uses is this kind of structure, try colon. So what you do is whatever is in this indented try block, you try to do. So we've defined two variables, y and x, and we try to define a third variable called ratio, which is y divided by x. Now, obviously, this is not going to work, right? So what do? You put in an except block after the error and do something. If you didn't have a try except block, the program would simply come to this point and give you a 0 division error and stop. Okay, but you may want to do something else. For example, you may, if y over x is 0, you may want to define ratio as y divided by x plus 0.00001. Okay, or some very small number like that. So you may want to go on in your program without stopping by dealing with the exception, which you do in this except block. So in the except block, what it does is it tries to do this. If there is an exception, it stops the execution of the try block and jumps directly to the execution of the except block. Okay, and here our except block is, it just prints divisor is equal to 0. And in this case, with our values of x and y, this is what the output that this code snippet will give you. So just like you use assert, also try to use try and except wherever you can. So the overall structure of try and except is like this. Try to do some processing, but except when you have some error. If you have some error, respond to this particular error condition Okay. And you can also do some additional thing, which you can say that raise some other error. Okay. Which you can then respond in another try except block and deal with it. Let some other piece of code handle the error. What is the main advantage of this kind of try except syntax? Those of you who have programmed in other languages like C or Fortran will be able to appreciate this instantly. What try does is that it gives you what you want to do at the top. You don't have to read through a lot of error trapping code to find out what your code is actually doing. Whereas in languages like C or Fortran, what you will typically have at the start of the block, for example, if you're expecting to have a float number or a positive float integer, which is non-zero and so on, you'll have to check at every step, is this a float? Is it positive? Is it this? And so on. You'll have blocks of code just doing input testing, right? You read, suppose you're reading data from a file and you expect to have 100 lines of 10 columns each, right? What are you going to do? You're going to read the file, then check whether there are 100 rows and then 110 columns and so on. Then you start processing the data. Here you don't do any such thing. You just try to do it, and the exceptions, of which there could be many. So you can have multiple except blocks, each tagged by its own error. So you could have potentially, like, for example, if you're trying to open a file, maybe that file is corrupted, it's of 0 byte length, or it's not present, etc., etc. Each of these will throw a different error, which you can handle using its own except block. Now, there is also sometimes you want to have, suppose you have an exception, you try something, and whether you succeed in the try block or whether you have an exception and therefore have to run an exception block, an except block, sometimes you want to close things and you want to have a block called finally. So Python provides that keyword called finally. So here we are trying to open some file for reading, okay? And we are trying to do something with the file. Perhaps we succeed, perhaps we don't. But whatever happens, at the end, you want to close that file head, okay? And that is something that is provided here via the content of the finally block. Remember, finally should also be indented, okay? Here it's not indented, even the try block is not indented, but both of these need to be indented. If you don't know what exception to expect, okay, you can just have a try and except block without specifying the error that we have specified here, okay? So you can try to open some file and accept file not found error, and then it just prints your specified file is not found, right? So that finally block is also, this except block is also can be used with or without specifying the error that you expect to get while in your try block. There is one more construct which is known as the for else construct. So we have looked at if, else, if, else, and we have looked at the for loop already. But what we have not encountered here is the for else construct. And what that construct does, it only comes into the picture when there is a break statement inside your for loop. And it is this break statement inside your for loop will pull you out of the for loop. And the block, the else block in the for else block, in the for else construct, is only executed when no item of the list is equal to 3, which means the break is never used. If the break is used, then the else will not run, right? So in this case, is it going to print out anything? No, because it's going to break. Only when the entire loop is run without the break getting operationalized, only in that case else is will run. So for example, if I want else is to run here, I could say if I equal to 7, for example. Since 7 is not in this iterable list, okay, obviously the break is never going to get operationalized. If I do that, then it will print this block is only executed when no item of the list is equal to 7 in this case. Yeah. Okay. Then related to this whole idea of sort of doing something, opening and closing files, etc., is something known as the with statement. And what that with does is that it's something like the try except, but it's more elegant. Okay. With open output file W as file dot write hello world. Okay, so you're trying to write to that file handle, right? And then we print, no need to explicitly close the file. This has been taken care of with the with statement. The with has actually taken care of. And that is what gets printed. So if you run this code, it'll open a file for writing. It'll write hello world to the file. Of course, this will be a new file that will get created because of this W option. And we don't have to close it. So it becomes somewhat more convenient than opening a file handle and then explicitly closing it. So if you're not used to the C way of doing things, I encourage you to open and close, open files with the with statement so that you don't have to ever explicitly close the file handle. Let us now move on to a very important area, which is called variable scoping. Okay. So which means if you define a variable somewhere, perhaps inside a function, where is it available? Is it available in the whole program, or is it available only in that function, and so on? So here we've done a simple, we've defined a couple of functions. One to define the area of a circle with radius r, and another to find the volume of a cylinder with radius r and height h. So we defined area, which is just pi r square, of course. Since we had done an import math on top, when we used math.py inside this function, the name math was known. It had already, the namespace had already been imported. We didn't have to do an import math again inside the function. That's not required, and that's not recommended. Fine. So there's no problem with this function area. Now, if you try to define volume, there's no problem here, because again we are calling the function area, but by the time the interpreter reaches the volume function, it already has area nicely defined, so it knows what area is. So you can use the area function over here, right? And h, of course, it gets from the calling function. So now, if I say volume and I call the volume function, everything is known because volume function has been defined in the code above. Volume function uses a function called area, which has also been defined even before. And area uses the built-in module math, which has already been imported. Now, if you try to change the order, like if you take the import math and put it below define area, right? Below the area function, this program won't work. Similarly, if you try to move volume above area, the program won't work. Okay. So it's very important that you know what variable scoping is. At the simplest level, if you just have one big file, then everything that is used should be defined above it in the program. This is very natural behavior. Those of you who have again programmed in programs like Fortran and so on, unless you know what a particular variable value is, you can't use that variable in code that comes afterwards. Right. Local variables inside functions. So by definition, something, unless explicitly defined to be global, remains a local value. So let us look, here we have defined two functions, f1 and f2. And f1 simply prints x, okay. F2 sets x to a string called local x and then prints x. Now, we have set x equal to the global x string. It has the same name as the x inside the function. Now, if I say f1, okay, it's going to know the x that is defined while calling this function, and it's going to simply print the value of x. And x has been defined as global x, so it prints global x. That's this function call. Then I do print x. Of course, nothing has happened. X itself has not changed inside the function. So it's going to again print global x over here. The output of print x is global x. Now, when I run f2, the function f2, I call it. Remember, all functions have to be called with their name followed by parenthesis, which may or may not contain any arguments. When I do that, it prints local x when I call f2. Because in f2, what has happened is within the function, x has been reassigned to local x. So it prints it as local x. Now, if I do print x, it still prints it as global x because only within the function f2 has the x been redefined. Outside, it still has the value global x. Okay. So please study this code carefully at leisure. Try changing some things and see whether the behavior is what you expect or not. So this brings up to us to what is called as function scope. Functions provide what is called as a nested namespace or scope, and these name references always search for 4 scopes. L is the function's local scope. Then it searches for the scope of enclosing functions. Then it searches for the module's global scope. And then it searches for the built-in scope. So suppose I write x is equal to something, or if I do print x inside a function, it will first see whether x has been defined inside the function itself, that same function. If not, it will look for whether x is defined in the function that is calling this function, or within the function that is calling the function that is calling this function. Right? Remember, functions can be nested. And if it can't find it, it will look in the module's global scope. Right? So modules are your programs. global scope? Has it been defined somewhere before any function gets called or defined? If not, it will look in the built-in scope. The built-in scope is always available. So the print function, for example, is available as part of the built-ins module, and you don't have to define it again. It's there. It's always available. Names assignments create local names unless you use the global statement. Okay, because of the structure or the order of in which a namespace is searched for the definition of a function, these are the scoping rules. If you create a function in your main program that has the same name as a built-in function, then your function, for example, if you define a function called type, which has the same name as the built-in function type, this will override the built-in function, leading to unexpected issues, because you have redefined type, but nobody expects you to redefine type, right? So if you want to use a variable, a method called type, it has to be encapsulated into your own module. So you can have my module.type or my module.print, which prints things out exactly the way you want. No problem. But please don't put it into the global scope. Okay, put it into the within the module's local scope. Never try to rewrite it. And it's generally bad practice to rewrite something with the same name. So in general, please don't create functions with the same name as built-in functions. Now we come to the global statement. For sake of completeness, I'm talking about global, but in reality, I have not used global in my code. And it's almost always a bad idea. And it is one of those things in Python that make debugging harder. So please avoid globals if you can. And this is not a statement that is made only in the context of Python. In other programming languages like Fortran, for example, again, there they will tell you that try to avoid global variables. Okay, so we've defined a function f3, and within that f3, we've defined a function called a variable called x, which we have defined to be global. Now we assign x is equal to local x and we print it. Now in the main program, so this is the end of our function block. In the main program, we said x is equal to global x and we printed x. That of course is global x because we just defined it. We even haven't called f3 at all. When you call f3, what happens is the global x is defined and the global variable is assigned a value of local x and then it is printed. So when I call f3, it's going to print local x. But now if I print x in my main program, now because x has been defined as a global variable here, it's going to print that local x value over here. Okay, so if you're confused by all this, that's a good sign, because you know that programs which use global variables become harder to debug because you don't know what is what. So please don't go in this direction. You can safely avoid use of globals. Now a bit about how arguments get passed to functions, which are called passing rules in Python. Immutable arguments act as if passed by value. When changing mutable arguments in place inside the function, the object is changed outside the function too. These are, so I'm going to illustrate these 2 points with examples. So don't worry about it too much. You can come back and read later. But I'd like to remind you that There are certain data structures in Python which are immutable, which means they can't be changed. Numbers, for example, strings, tuples, etc. On the other hand, elements of lists, of dictionaries, or even NumPy arrays, which we will encounter in the next lecture, these are mutable objects, okay, which means they can be changed. And therefore, the passing rules apply differently in these two cases. So let's say we have a list, which is of course a mutable function argument. Okay, so I define my list as 1, 2, 3, right? And I want to extend my list. And in order to extend the list, I define a function called extend list, right? And it takes one argument, which presumably is a list of objects, a list that you want to append or use that list to extend your existing list. So when I do extend list, all it does is takes that argument and applies the extend method of the list to it and adds the elements 4 and 5 to the my list. So if I call the function extend list my list, okay, and then I do print the length of my list, and of course then I print my list itself, you can see that the list got extended, which means although I changed the value of my list within a function, it got extended globally, okay, outside the function. And it did that because the list is an mutable argument. Okay, so it's a mutable object. On the other hand, a float variable is not a mutable object. It's an immutable object. And when you use a float as a function argument, something different occurs. So we've now assigned the variable a to a float, right? And I define a function called float to string. Okay, it takes some variable as an input, and all it does is it replaces the value of the variable that came in with string variable. And we saw that the string function is a typecasting function, which will take whatever argument it got and convert that to a string. And then, of course, I simply return the variable. Now, if I do float to string a, right? And I do print type of a, that type is still float. Okay, because what has happened is a has not changed, and within the variable, although I passed a to the function, because a is an immutable object, right? It didn't act, this var is equal to string var, converted it within the function, okay, even returned it, but didn't change the value of a. So a remains a float and it still has a value of 5.0. Then I have this print with no arguments, just to leave an empty blank line. But now I call the function again, float to string, with the same argument a, but this time I capture the return, this var which is getting returned from the function, I capture it in a variable called b. And then now if I print b, the type of b, this is now a string. If I print b, it again prints 5.0, but remember this b is now a string. Of course, the print, whether you print a float number or a string, it just prints it the same way. It doesn't quote it or anything. But this object is a string. B is a string, whereas A remains as a float. So here, by use of simple code snippets, we've demonstrated how the behavior of a variable that is supplied to a function, how it changes depends on whether it's a mutable object or an immutable object. So be really careful about this. Now let's look at the dell keyword in Python. This is used to delete objects in Python. Since almost everything in Python represents an object in one way or the other, the del keyword can be used to delete a list. It can be used to slice a list, to delete a dictionary, remove key value pairs from a dictionary, delete variables, etc. So I've given this example code here. Del A means delete the variable A. Here you, from the Redshift dictionary, delete the entry for M31 when the key is M31. Here mylist2 means delete the third element of the list mylist. And other list, this is a slicing operation. It says that from other list, delete element number 3 with the label 3, which means the fourth element, onwards up to the end, delete all the elements of other list except for elements number 0, 1, 2. What does del do? The del frees up memory. If you have very large arrays that are not going to be used in your analysis going forward, you may want to just delete the array so that some memory on your computer gets freed up. The memory does not get freed up instantly in Python. There is an process that continuously runs when you're running Python, which is called the garbage collection process, which is identifying arrays and other variables that are no longer being referenced and therefore should not need to exist, and they get cleared up. So when you del the array, it may or may not get freed up instantly. You may need to run the garbage collection module and the functions within that explicitly to delete your arrays. Now we come to another function called is. Okay. Is used to compare two objects and to find out whether they are the same object or not. Now I defined a is equal to 5, b is equal to 5.0. So obviously one is an integer and the second one is a float. If I do print a is b, that returns false. A is b is false over here. And that is because a is not the same object as b clearly. But if I say print a is equal to b, that returns true because the value of a and the value of b are the same. Okay. So how to choose variable names? Names of variables can contain upper and lower case English letters. Strongly recommend to use lowercase English letters wherever possible. Underscores are allowed, they're useful. And you can use the digits 0 to 9, but the name cannot start with a digit. So you cannot have 5A or as a variable name. Nor can a variable name be a reserved word in Python. Okay, we'll come to reserved words in a second. So you're not supposed to use reserved words. You're supposed to choose descriptive variable names, names that explain the variable's role in the program. Okay. For reasons of brevity, I have used the variables a, b, c, etc. quite extensively in the code snippets presented in this course. But please, when you write your own programs, don't put variable names as a, b, c, x, y, z, etc. That's a bad idea. Well-chosen variable names are essential for making a program easy to read. Python makes it so easy to write readable programs. So why don't you do your share and use variables that make sense, because that will make your life easy. You'll find your programs easy to debug and easy to extend. Well-chosen variable names also reduce the need for comments. So like if you choose a variable called pi, for example, everybody knows what that means. If you choose a variable called capital G for Newton's constant, you don't have to say Newton's constant explicitly. Okay. In the context of variable names, there was one little thing that I wanted to add. There was a question in one of our discussions whether Unicode names, we said that Unicode names, Unicode strings can be freely used in a Python program. The question was, can Unicode variable names be used? And the answer to that is yes in Python 3. I was actually not aware of this. So here I've defined a variable name in English, then variable name in Tamil and Hindi and so on. I've defined a list in Marathi, and I've added these three numbers together and printed them. Of course, that works. I've iterated over the list, my yadi, and printed each element of the yadi, which being a list, can contain heterogeneous objects. So it contains 3 integers and 1 string and so on. So you can use that. But again, if you look at the PEP, the recommendation from just the readability point of view is that you try to stick to variable names in English. But if you really have to, you can use Unicode variable names if you wish. Okay, so now we come to the list of reserved words. These are the words that cannot be used as variable names. Okay. Now, what I've done here is I've marked in red the reserved words that I have not discussed in this lecture so far. And those are only 4, class, lambda, non-local, and yield. Okay. With this, but everything else has been covered in the course of just about 4 lectures. With this, we have covered essentially all of the core Python functionality from the point of view of the various data structures and conditionals and loops, etc., that are available within Python. We've seen them all. So if you have reviewed the lectures carefully and you have practiced changing the code that in the Python notebooks, you can claim now that you are set to program in Python. Of course, becoming an expert programmer is going to be a long journey. And we are going to get you started on that journey over the next 5 lectures and in the 2 tutorials that are to follow. But remember, it's a huge world. The Python standard library itself is large, and the vast world of third-party modules now awaits you. So congratulations if you have gotten this far. You've made a fairly successful journey. So assignment 1. Assignment 1 is nearly ready. Pritish has been working on it, and I've made some suggestions and modifications to that. And we're going to place it on the Moodle platform and on the website by tomorrow. Please download the assignment, take a look at it, and try to solve as much of the assignment as you can on your own. The assignment is based on all the material that we have covered up to today. There is nothing that you would need to install in terms of third-party modules, etc., to solve assignment 1. Assignment 2, of course, is going to be a different object, but that is coming some weeks later. Pritish will conduct a tutorial session, most likely on December 2nd, to discuss the assignment problems and their solutions. So please, without Googling, without you refer to these lectures, you refer to the notebooks, and try to solve every problem in your assignment. Remember, programming is always about the doing, not about the knowing. You may know many things, but unless you practice them, know them, you will not grow better. So here's a brief outline of the second half of the course. We are now halfway. I've done 5 lectures. In the remaining 5 lectures, we will cover basically third-party modules in Python. We will start with NumPy and a bit of SciPy. I will talk about matplotlib, the main plotting tool in Python, and I will talk about the modules AstroPy and AstroQuery, which are astronomy specific. These two parts will likely happen in the last 2 or 2.5 lectures, which will be very astronomy specific. I must warn you here that the second assignment will be considerably more difficult than the first, and will have some real life, although simplified code interactions with real astronomical data. With that, we come to the end of this first half of the course and the end of lecture 5, and I'll stop here and take your questions.
It's a very naive question.
Yes, I can hear you.
Like, what is difference between like if else and try except these two things, like these two loop blocks? We use if else. Now we have learned about try except. So I mean,
Yes.
yes. So how is it different? I mean, I'm
see
using
you will come out of the try loop. Yeah. Let me try to explain. Right. If you have the try and except loop is only used when you expect to have an exception. It is not a conditional break in your program. When you expect something to go wrong, you put it into a try loop. Okay. Whereas the if else is a conditional, like if a is greater than 0, you do something with your code. If a is less than 0, you do something else. Okay. So these are two pathways within your code. Try and except are not like that. Try and except are only built to handle exceptions. So in that sense, they're not at all. I mean, they may appear similar, but there is functionally no similarity.
Okay, thanks, Yogesh.
Sir, I have an observation and a couple of questions. This is regarding the try except blocks. The observation that I have is that this try except block, I find that it is actually similar to the try catch block in C++. The try catch statement in C++. I felt it was very similar.
That is correct.
And I have a couple of questions regarding this. The first question is...
in fact, many syntactical things in Python, No, sorry, I was just trying to say that many syntactical things in Python borrow from C or C++, just to make it easier for C and C++ programmers to migrate to Python. That's why you'll see a lot of syntactical similarity between the two languages.
Okay, sir. So I have a couple of queries regarding this same try except.
So please go ahead with your question.
The first question is, in one of the previous classes, you had shown us how we can use the dir function to list out all the available functions inside a module. So the first question is, do we have something similar by which we can find a list of all the available exception types? That's my first question. And the second question is, so suppose I have a try catch block. So in that, try except block. And in the except block there, let's say I have two except blocks for catching two different exception types. Can I have a third except block where I can catch generic, anything else, any other exception apart from these two, any generic other exception? Can I have one more block for that?
Yes, you can. Okay, but that should come last, because that will only get triggered if the first two exceptions. Presumably that's the behavior you want, wherein you want to catch 2 or 3 named exceptions, and if something else goes wrong, you want another except block to run. Yeah, you can have, that's allowed. You can have any number of except blocks with named or unnamed errors, and it goes through them in sequence.
Sir, is there any way to find the list of all available exceptions?
Did you have any other question? I think you had a second question.
Yes, sir. The second question
is list of all available exceptions. So there must be a, yeah. I got your question. So I don't know. There must be some way of listing exceptions programmatically, but I don't know if what that is. So all you should do is Google for. So it's obviously there in the documentation. So if you Google for comprehensive list of Python exceptions, you will get them. But remember, there won't be a single list of exceptions, because if you're opening a file, you can have a file not found exception. But if you're dividing two numbers and the divisor is 0, so the 0 division kind of exception will only be in that context. So there is really no way of having an exception for every object or for every operation in one long list, because that list can be infinitely long. So you will have, for the built-in standard modules, the documentation will tell you for any kind of function or object, what are the kind of exceptions that it can throw. But I don't think it makes sense to have one page or one list of exceptions. There must be a list for a given module, for example, what are the exceptions that it can handle. Okay, but I don't recollect how that can be done programmatically. But certainly, if you look at the documentation of, for example, if you look at the documentation of the float object, right? It will tell you exactly what exceptions the float operations can throw. So basically for floats, there can either be overflows or there can be the 0 division kind of errors. So those will be listed in the documentation for float.
Thank you, sir.
So I'll just go through the questions on the chat. The question is, one of the questions is compares only object type or both object type and value? Okay. In fact, it compares much more than that. It compares whether they are the same object or not. So if you have a variable that points, if I say a equal to 5 and b equal to 5, okay, remember a and b are variables, but they are basically pointing to the float object 5. So there, if you print a is b, so why don't we, I'll just stop share and actually illustrate what I mean. So here I've defined a is equal to 5 and b is equal to 5. Now a is b is not just, it's not, a and b are like identical objects, okay, because they're both equivalent to the object 5, not to the number 5, right? Remember, we once said L is equal to something and M is equal to L, then you change L, then M changes as well. Okay, that's the reason. So now if I do A is B, that obviously returns true because these are both the same object. And B is equal to 5.0. If I then do A is B, that returns false. But are they equal in value? That is true. They're different objects, but equal in value. So think of is as comparing the identity of two objects rather than just their value. Are we able to define exceptions? That's a very interesting question. And the answer is yes. You can write your own exceptions, which can build upon the exceptions that are there. So for example, if there is a file not found error and a file is unreadable error, you can define a exception of your own, some problem with the file, which is an OR of the file not found error or file not readable error, right? You can OR it and make your own exception. It says some problem with file error. You can define your own errors within your Python program. Can we use is to compare two strings? Okay, that also is a very interesting question, right? If they have the same value, what do you think will accept? But best is to try out. So I will go back now to sharing my screen. And I open my Python. So I have a string called hello. And is it the same as hello? Okay, so here it didn't write it. I can do print hello is hello. Starting is with a literal. Yeah. Did you mean equal to? So it is just warning me. It prints out the value. Is hello? Yes, because there is a string object called hello. Now remember, since this is case sensitive, this returns false. Hello is capital hello. No, that's not, obviously, returns false. Even if I put a space, I go back to small hello and I put a space after this hello. Hello and space. That also is false. Right? So the is can be used to compare strings and so on. Let this. So if I go back to the chat, yeah. Yes, so you can definitely use is to compare two strings. There is absolutely no trouble with doing that. There is one more question. Can we use try except in if else loop? Yes, absolutely. You can. They're all independent structures. Everything can be nested. You can use try except inside an if else. Okay. You can also use an if else inside the try except, or multiple try excepts inside one if else, or whatever. So there's no limit to the amount of indentation. But in practice, about 3 or 4 levels of indentation is all you will need. Yeah, so definitely you can mix and match any of the structures. You can have a for loop inside a while loop. You can have a while loop inside a for loop, whatever. There's no limit. Okay, are there any other questions in the chat or on audio? Otherwise, we are ready to start.